Let me start. I hope I'm not going to disappoint you with my talk. With a breakthroughs in immunotherapy and Leiomyosarcoma. But I've been doing immunology for a long time. I remember when I was doing my PhD in immunology, people were laughing at me and saying, "What do you need immunology for?" They say. And even when I started doing my oncology training, we said, "Oh, you need to concentrate on chemotherapy. Immunotherapy is of no use for patients." Of course, these days everybody wants to use immunotherapy, luckily, and luckily this all changed. But let's start from the beginning. I'm gonna give you introduction, and hopefully it's not too basic, but to say what's immunotherapy, how it's different from other therapies, in which direction we are developing treatments. So first of all, what would be an immuno-oncology? So immuno-oncology really focuses on using the power of the immune system to detect and destroy cancer. So I have to say, very often when patients come to me and talk to me, especially for the first time, I might be disappointing for them because very often say, "Oh, you talk about immunotherapy, so what can I do to boost my immune system?" This is a very common question which you get from the patient. What can I do to boost my immune system? What's disappointing, when unfortunately majority of patients with cancer have a completely perfectly good immune system. You are not reporting that you are getting pneumonias or flus or recurrent infections. So you have a perfectly working immune system, and despite that, the cancer is growing. So if we go philosophically, it's not that your immune system is failing, it's that the cancer found a way to outsmart perfectly working immune system, and that's why the boosters for the immune system, what we naturally use, make it to get stronger. When we have a flu season, we are unlikely to work with your, to help with your cancer. Having said that, on rare occasions, people do have immunodeficiencies, and then this can predispose to cancer, but this will be probably about 2% of patients with cancer. It's not a typical patient population. So why do we like immune system? Immune system protects us from all the infections. It's very successful. We are not dying of infections. We have our vaccines that protect us from so many infections that allow us to live longer. Now, immune system is very specific, so once remember something to recognize and eliminate, it can virtually recognize almost infinite number of different antigens. It can be adapted, so depending on the changes in the body, changes in the environment, our immune system can adapt to that. And on top of that, the immune system has memory. So you were vaccinated against the virus as a child, but this memory stays with our immune system for the rest of our life. It's an ideal anti-cancer agent, I would say. It's a diversity, so when we look at our most important immune cells, T cells or B cells. T cells are the ones who usually lead to the destruction of cancer. If they work, we have 10 to 18 power, T cells in our body, and we have more even B cells producing a variety of monoclonal antibodies, against viral or infectious agents, but possibly also against cancer. So even if there's a small difference, our immune system, comparing what's normal and abnormal, can detect this difference and elicit an immune response. This is one of the problems why immunotherapy has been very successful generally recently in cancer, but why it's not so easy to develop immunotherapy, as it is probably much easier to develop vaccines against viral infections. what do we need? We have immune system. When we think again philosophically about it, why do we have immune system? Generally, we have immune system to protect us from infectious agents. So this was the goal why why we have immune system. It protects us from outside. So the goal of immune system is to get rid of what's foreign, but not to get rid of what's self. So if a virus enters our body, immune system says, you don't belong here, let me get rid of it. If a bacteria enters our system, you don't belong here, let me get rid of it. But cancer comes from our own cells. So cancer is abnormal, can take our lives, but in 99% it resembles our normal cells. So generally speaking, immune system says, oh, it looks like you belong here, you look like you are from this body, I'm not gonna get rid of you. And luckily there is this small percent of differences and we are trying to use it for our immunotherapeutic approaches. So it is, I don't want to sound hopeless, but that's why it's much more difficult to get rid of cancer using immune system and to get rid of infection. Am I doing something wrong? Oh. Okay. So the next question is, how do, and again I'm going much more into detail, but hopefully it gives you a little bit of understanding of the whole process. How does it happen that the immune system gets rid of cancer? So it's a multi-step process. To get rid of cancer, it's not just one step. You will see on the left side of the screen where it says tumor. First, the tumor has to release an antigen. So release something that's differs the tumor from normal cells. Then here on my graph, we don't have a pointer, but on my graph we have something that's called dendritic cells. These are specific cells that pick up this antigen and they process it. They migrate from the site of the tumor and they travel to the lymph nodes. We all have lymph nodes all over our body. When they sit in the lymph nodes, then the immune cells called T cells, they travel through those lymph nodes and say, is there something that these dendritic cells present to me that can activate? And this is the interaction that you see between the T cell with a T cell receptor and dendritic cells. Once the T cell recognizes it, it gets activated, it activates itself, it proliferates, it expands in number, leaves the lymph node and starts seeking for the same antigen somewhere in the body. When it finds it on the cancer cells, it releases specific enzymes to lyse the cells and destroys cancer. But what it also shows, as I say, it's easy process, we understand what all the steps is, but cancer can evade the immune system by blocking different steps. As we understand immunology better, we see that, for example, some cancers don't release enough antigens. If they don't release them, the cells, the initial step cannot start. Or they release the cytokines or proteins that can inhibit maturation of dendritic cells or presentation of the dendritic cells to T cells. Or when the T cells are in the lymph nodes, there are specific markers on the surface of those T cells that can block our interactions or inhibit interactions, or then the cells will never get activated. Or the cells may get activated, but they are not able to penetrate into tumor and they cannot get into the tumor to eliminate the cancer. So what we see that it's not that the cancer is so smart, but if the cancer did not have this defense mechanism, we would never know that we have cancer in our body, because these cells will be immediately eliminated by our immune system, would never cause us a problem. So if you already have a tumor in our body, it means it must have evaded the immune system at in one of these steps. So let's look right now. Let me actually go back here. So let's talk a little bit about what we call PD-1 or PD-L1s and CTLA-4 blocking antibodies. I'm going to talk about the mechanism a little bit than anything else right now. Probably right now on the market we have about 9 PD-1. I lost track of it, but you know, about 9 PD-1 blocking antibodies that are approved for treatment of different cancers. I started my career and I still continue. I started my career in melanoma. So in melanoma, we knew that immunotherapies can work. We knew it for about the last 40 years or so. So initially we thought, you know, oh, there must be something special about melanoma, maybe kidney cancer, which was also reacting more with the immune system. But these two cancers are very different from other cancers. And these are the cancers that interact with the immune system, but the rest, our lung cancers or breast cancers or prostate cancer or sarcomas, they don't interact with the immune system. And luckily I was proven wrong. So we see right now when we believe that every single tumor, every single type of cancer interacts with the immune system, but we may not have enough knowledge still to understand these interactions of a particular tumor. But it gives us some hope that if we continue research and understanding of interactions between tumor and immune system, we can break the code and use it for future to use the immunotherapy to treat our cancers. And one of these breaking codes was this discovery of these two molecules, PD-1 and CTLA-4. They were actually, PD-1 was discovered actually first, CTLA-4 later. Initial discovery was kind of abandoned of PD-1, and CTLA-4 was developed, and then we returned to PD-1 as a target, which is right now appears to be a better target in immunotherapy. What are the functions of these molecules? These molecules, and it's a very complicated slide, but for simplicity, I'm telling that these molecules are natural brakes on the immune system. And we often use this comparison to a car. When you drive your car and you want to stop your car, it's not enough to take the foot off your accelerator. Eventually your car would stop, but you would cause a lot of damage before it happens. You need to have your brake to push on it to stop. So this is what happens when a flu virus enters our body. We start getting our muscle aches and fevers and chills. This is the immune response against the virus. But the virus is gone, but if we don't have a brake, we would continue having fevers and chills and muscle aches. So we are pushing on the brake to stop the responses. But it can happen that the cancer can use the same brakes to evade the immune system. Our immune cells want to destroy cancer, but the cancer upregulates or stimulates the natural brakes, and then there's no response, like we are stopping response against infectious agents. So I'm not going to go into details of this, but we know right now that the function of CTLA-4 is more important in the lymph node, when we have an interaction of the cell, the dendritic cell, which I mentioned, with a T cell. And this is where the initial activation occurs, and this is where the CTLA-4 blocking antibodies, such as ipilimumab, which was already mentioned, would work. And once the cells get unblocked or activated, they travel to the tumor environment, and when they encounter the tumor may have a PD-L1, which is a ligand, a protein that connects, and use it to inhibit our T cells. So they got into the tumor environment, they are ready to destroy it, but the tumor has on the surface a molecule that pushes on the natural brake on the immune system, and the cells are not able to destroy the tumor. So this is where our PD-1 and PD-L1 blocking antibodies work, but they block this interaction so the immune system can be unopposed. So as I say, right now, some of the PD-1 blocking antibodies, such as, for example, pembrolizumab, have, I think, 18 indications, approved for melanoma, kidney cancer, bladder cancer, some types of lymphoma. They are approved for esophageal cancer, for gastric cancer, and so on, so on. They are not approved for sarcoma. And this was the original trial of pembrolizumab in patients with soft tissue sarcoma. And as you see, in this trial had about 40 patients, a little bit fewer than 40 patients. You might not be able to see, but there was was divided into 4 groups, and one group was Leiomyosarcoma. And when we look at maybe on the right side, each curve, each line is a separate patient. And if the line goes down, it means the patient's tumor is shrinking. If the line goes up, the patient's tumor is increasing in size. So if you see the red lines with the ones which are shrinking, is something what we call undifferentiated pleomorphic sarcoma. Leiomyosarcomas are dark blue lines, and unfortunately in this clinical trial, all patients had some increase in the size of the tumor when pembrolizumab was given. Because of the results of this trial, it was only 10 leiomyosarcoma patients. Further development of pembrolizumab as a single agent in patients with leiomyosarcoma was stopped because it was not sufficient evidence that would be beneficial. We have a different clinical trial, and again, when we look at the clinical trials, this is very so confusing for oncologists, and even probably more confusing for patients, because we always see, oh, this chemotherapy or this immunotherapy worked for this patient. Doesn't mean it's going to work for everybody. And very often in our sarcoma clinical trials, what happens, we enroll a very heterogeneous group of patients. We enroll patients with leiomyosarcoma, but we might be enrolling patients with angiosarcoma, with liposarcoma, or other types of sarcoma. And we get the result of a trial, and now you have a patient in your office with sarcoma A, and say, can I apply the results of this trial to this particular patient? If, let's say, patients with this type of sarcoma were not included, about only a small percentage of the trial, are the results of the trial really applicable to my particular patient that I have in the office? So in this clinical trial, again, this was a combination. It had 2 arms. On the left side, you see patients treated with PD-1 blocking antibody called nivolumab, and here on the right side, a combination of nivolumab and ipilimumab. And as you see over there, I pointed towards for the lines. Here you can see the bars. If the bars are going, each bar is a separate patient. If the bars are going down, the tumor is shrinking. If the bars are going up, the tumor is increasing in size. So as you see, you saw some shrinkages in both arms. Maybe on combination in this clinical trial, you saw a little bit more shrinkages. But when we look at details, in all the group of patients, in the first cohort, there was 1 non-uterine leiomyosarcoma patient that responded to the treatment, and if this response, this benefit lasted for 15 months. In the second, we had 2 leiomyosarcoma patients. Both of them, if they responded, the benefit was very good. The benefit of 55 months is what? 4.5 years. This is a wonderful benefit. But as you see, these were few and far in between with all the patients that are enrolled in the trial. So this trial gave us information, that yes, there will be leiomyosarcomas that can respond to immunotherapy, but unfortunately, it's not going to be majority of the patients. It will be definitely minority of the patients. So people are trying to say, okay, let's be more homogeneous. Let's not increase, let's not do all the sarcomas. Let's be more specific. They say, okay, here let's look at 12 patients with uterine leiomyosarcoma. Again, it's a different curve. Here you say when we start, it means that 100% of people have disease under control. As the curve goes down, it means fewer and fewer people have disease under control, but disease grew back. So we see in this population, when the nivolumab was used, there were no responses, and the median time to take the patient off the therapy because the therapy did not work was only 2 months, less actually than 2 months. Which clearly showed us, again, we have this single patients that benefited, but there will be, in leiomyosarcoma, unfortunately, there's a few patients who benefit. So I say, can we do it a little bit better? And this is a new drug, which is they are not, neither of the drugs is approved, but balstilimab, the second drug, is a typical PD-1 blocking antibody, similar to the ones I mentioned, like pembrolizumab and nivolumab. It's just developed by a new company. But botensilimab is CTLA-4 blocking antibody, so it's similar to ipilimumab I mentioned, but this one is modified. So there was some evidence, for example, in colon cancer. We don't think that colon cancer is very responsive. 90% of colon cancers are not very responsive to immunotherapy, but we did see some response to the use of these antibodies in colon cancer. It's just, so it really shows it has the same target, but the scientists were looking and saying, can we improve the inhibition, that if we use even the same target, can we do better? So actually, there were results of this trial presented, and we generally see a little bit more shrinkages. But again, so this, when we look at what we call response rate, which is here on the top on the right side, it was 23%, which would suggest that 1 out of 4 patients benefit, which is a good result. But when we look in more granular, this were not, majority of them unfortunately did not have leiomyosarcoma. We know, based on this research, we know that some sarcomas are quite responsive to immunotherapy. Angiosarcomas are responsive, undifferentiated pleomorphic sarcomas, myxofibrosarcomas. These are the sarcomas, the alveolar soft part sarcoma, very rare types of sarcoma, only 50 cases a year in the country. These ones are the ones that have a very good chance of responding, but the more common sarcomas like leiomyosarcoma or liposarcoma, the responses are much less common. So, and this is also an attempt to challenge in his clinical trial, say, can we make it better, Can we make it better? I say, can we combine the chemotherapy and immunotherapy? Yes, so we can do it. When I talk about the results of these different clinical trials, I always tell the patients that you have to interpret these results with caution. Because unless we have a comparator arm, 2 groups that we can compare, at the end we cannot fully say how much of the benefit came from chemotherapy and how much of the benefit came from combination of chemotherapy and immunotherapy. Because we know that chemotherapy alone can help patients with leiomyosarcoma. So if you have this combination, are you really improving, or you would achieve the same with chemotherapy alone? So for example, you already heard the drug gemcitabine, which is we commonly use in the treatment of patients with leiomyosarcoma. Here was combined with pembrolizumab. 19 patients with leiomyosarcoma, actually only 5% of patients benefited. Then we have eribulin, another chemotherapy used mainly in liposarcoma. But in this combination clinical trials, there were 19 patients with leiomyosarcoma. Only 1 patient benefited out of 19. Then we have doxorubicin, dacarbazine plus nivolumab. Now we have very active chemotherapy of doxorubicin and dacarbazine as a backbone, and we are adding immunotherapy. Here, almost half of the patients benefit. So this is already something what we call hypothesis generating. I say, maybe there is some activity because the response of 50% is much more than we would have expected from chemotherapy alone. So these are the approaches that might be worth taking further. Like the previous 2, I would say, let's abandon that. This is not sufficient. This is not what we do. So as we were talking about clinical trials, when we develop, we have a new concept. We say, let's run on a small number of patients because we don't see responses, let's not take any further. And the gemcitabine and docetaxel in combination with another PD-1 blocking antibody, here the response in leiomyosarcoma was 33%. Here I would ask, I don't know how good it is, because gemcitabine and docetaxel alone can give about 25% response rate. So this might be just that we selected the patients when they gave this magnitude of benefit. And then we have nivolumab and trabectedin. The trial was in not only in leiomyosarcomas, but there were 28 patients with leiomyosarcoma, and we don't have a detailed response just in leiomyosarcoma. In whole population, almost half of the patients benefited. So again, this is the combination which is of interest, because I can't prove that this is definitely beneficial, but if I was selecting nivolumab trabectedin or nivolumab doxorubicin dacarbazine, this would be combinations of interest for further research. So what about targeted therapy? And I realized as I was playing with this buttons, I skipped the initial 2 slides. So let me talk about it now. Okay, so let me talk about, because there's an important question, what's chemotherapy or targeted therapy, what's immunotherapy? We already told you about principles of immunotherapy, how it works, when we are using the immune system. But philosophically, we can also think about if we use chemotherapy, if we use targeted therapy, most of the time it is a direct injury to cancer cells. Chemotherapy, we give a toxin and we hope that cancer cells are more sensitive to this toxin than our normal cells. We give them, we injure the cells, hopefully they die, hopefully not grow, and normal cells persist, and this is success of chemotherapy. Similarly, targeted therapy, and you can broaden the definition, but the typical is, we found a mutation in cancer cells, we have a drug that inhibits this mutation, and so we use this to target our therapy, direct injury to cancer cells. Immunotherapy, very often immunotherapy may not even bind to cancer cells. The drugs which we mentioned here, pembrolizumab, nivolumab, ipilimumab, they don't bind to cancer cells. They bind to the cells of the immune system and change this immune system in such a way that it could fight cancer. So it's indirect injury. The drug by itself is really not interacting with the cancer. It's the immune system that's doing its job. Right? We are expanding these definitions right now to other areas. We are sometimes using immune system to deliver the drug, and this will be to the cancer. So this will be combination of what we say of direct cancer injury with the use of the immune system. Yeah. I hope it's going to pan out, but yes, it pans out in many other cancers, in breast cancer, in some other cancer, this is a breakthrough. But in combination, so here I'm talking about combination of targeted therapy, pembrolizumab and axitinib. It's a wonderful combination in patients with alveolar soft part sarcoma. In leiomyosarcoma, one patient had only a response. Lenvatinib, pembrolizumab, there were no responses in this combination in patients with leiomyosarcoma. Cabozantinib, combination with nivolumab, ipilimumab, only 1 out of 10 patients with leiomyosarcoma responded. So again, I don't see any significant promise here. What we know, what we learned is, when we think about types of cancer, we can divide it into 2 groups. One which are inflamed phenotype. When you look at the cancer under the microscope, you see cancer cells, but you see the cells of the immune system all surrounding the cells. And generally speaking, we think that if you have this inflamed phenotype, these cells respond better to immunotherapy. Unfortunately, when we look at leiomyosarcomas, under the microscope, we see cancer cells, we see blood vessels, but we don't see many immune cells within sarcoma. And this is what we call non-inflamed phenotype. Because of that, we are trying to change it, and this is an example of otalimogene and parentvec. This is TVEC Dr. Chawla mentioned in combination with pembrolizumab. Can we bring these cells to the immune system by injecting the oncolytic virus, you ask, because TVEC is an oncolytic virus. So yes, we can bring them. It does not always result in responses. In all the sarcomas, we had 35% of patients who responded. Unfortunately, leiomyosarcomas did not respond. This is another trial. This is another method of therapy. This is not approved for leiomyosarcoma, but it's developed in myxoid liposarcoma and synovial sarcoma. So it's a very new method of therapy. This combination is not approved yet, and it will be approved probably very time soon. Can we do it like that, when we find the antigen or something which is specific for tumor cells, when we know it's on the surface or presented on the surface, and can we create a receptor on your cells of the immune system, T cells, and introduce to your T cells? If we do that, then your immune cells have a receptor that can recognize something on the surface of the cancer. So this is the principle of this adoptive cell transfer therapy. Patients' immune cells are taken from the body, modified in the lab to introduce receptor to recognize something from cancer cells. It's easy to say, it's really difficult to do, not the manufacturing part. But you have to realize that whatever is on cancer cells cannot be present on normal cells. Because if it's present on normal cells and you infuse the cells of the immune system will not differentiate, oh, this is cancer, this is not cancer, will be destroying everything that contains this protein on the surface. So yes, might be destroying cancer, but if the same is present on your heart, will destroy your heart too. So that's why it makes it again difficult, because cancer cells resemble our own cells so closely, but it's not hopeless. In some other cancers, as I say, in Immunotherapy, we are using an antigen called NY-ESO, and if you use this method, if you find the right antigen, now you see that almost in all patients the bars are going down. This is synovial sarcoma, different type of sarcoma, but this is something which in a direction which they say if we find the right target, we can be very successful. This is the therapy that was recently approved for synovial sarcoma, the same concept, and as you look at these curves again, each curve is a single patient. Some did not respond, but majority of the curves are going down. Going down means the tumor is shrinking. So this is kind of a summary of what I showed you about immunotherapy in Leiomyosarcoma. I probably was not overly optimistic with what we have right now, but this is, I wanted to be realistic. So we do see rare responses, but they remain rare. Combination of chemotherapy and immunotherapy may give higher responses. To confirm that this is successful, we would need randomized trials. But there's definitely everybody who takes care of sarcoma and people in the lab and basic researchers are very enthusiastic about progress in immunotherapy and further development. And there is hope. This hope I'm not giving you particular directions where we are going, but generally it's a concept where we are going. We will need a more personalized immunotherapy. We achieved whatever we achieved right now, but can we do more personalized? Can we look at the tumor and understand? I'm mentioning that some of the tumors are inflamed when we see that they interact with the immune system, and if they are so doing so, then maybe pembrolizumab, nivolumab, with PD-1 blocking antibodies would be sufficient. But some tumors are not interacting with the immune system. We don't say immune cells, so we have to go beyond that. Do we need to use cytokines, like interleukin-12? Do we need to use some other targeted therapies or macrophage inhibitors or some other cells inhibitors? So there is a strong in the lab, still in the lab, not in the clinic, strong push towards understanding what type of interaction is between immune system and environment. You know, how can we affect why? If this person, the sarcoma is growing very fast and they are dead in 6 months. If that person's sarcoma is growing slowly and 5 years later they are still alive, you know? So it's not only sarcoma, but it's also our body, how it is. And maybe we need to generate specific cells with use of the vaccines. T-cell receptor therapies, this is what I just showed you, synovial sarcoma, or other molecules. I'm not going to go to details. So there will be progress. We are not there yet, but there will be progress. Thank you.
Thank you very much, Dr. Chmielowski. Okay, so again, yesterday we did start preparing some questions for you, and then if there are any questions from the room, then we'll also come to the room to ask some of the questions. But before we do that, so the first question is, what is the difference between immunotherapy and targeted therapy?
So I just kind of mentioned that so targeted therapy is a direct injury to cancer cells. Immunotherapy uses the immune system, so it's our natural defense against infectious agents, to fight cancer. So this is our simplicity.
Thank you very much. Then the next question was, how does one qualify for immunotherapy for specific LMS?
So,
and can immunotherapy be first-line treatment?
yes, so immunotherapy could be first-line treatment. I have to say, probably in LMS, generally, how do we select the therapy for a patient? When we see the patient in the office, we say, which therapy has the highest chances to work? It doesn't mean it's going to work, but which one has the highest chances to work? So if I see a regular, or average, nobody's average, but a regular Leiomyosarcoma patient, I would say chemotherapy has a much higher chances to work than immunotherapy. And I showed you by percentages of success, you know. There will be those people who benefit only from immunotherapy and will never benefit from chemotherapy, but when you do measure odds, the odds are rather in favor of chemotherapy than immunotherapy is the first line of treatment. So you can do it, but is it the right thing, you know? So it's not like when you want to select the treatment that has the highest chance for success. But if a patient tells me, you know, never, I'm not going to do chemotherapy. So it's nothing that you cannot do it, but is it the smartest choice? And the second thing is, how do you qualify for immunotherapy? There is no specific qualifications. Again, what you buy, the question is it meaningful to give immunotherapy? What are your chances that you will benefit from this immunotherapy? So in Leiomyosarcomas it will be very difficult to find, but clear indications would say yes, you would be the one who is responding to immunotherapy. But sometimes I do differently. I say, oh, your tumor is not growing so fast. If we use immunotherapy, let's try for 3 months, see what happens. If it's not working, we'll switch you back to chemotherapy. Generally, I always start with chemotherapy, you know, unless there's a special request from the patient. But I say, at some point, I say, okay, this might be a good time to try immunotherapy. I say, you know, the chances are 5 to 10% that it's going to help you, but somebody will be in this 10%. So these are kind of the discussions we have.
Thank you very much. Is there a reason why you start with chemotherapy first?
So I start usually with chemotherapy first because there is a higher chances for response, you know. So again, it's always, we are using the ones that has highest chances. It doesn't mean that it's gonna work, and it doesn't mean that the next line of therapy wouldn't work if the first line didn't.
Thank you. Then we had another question, which is, can PARP inhibitors or aromatase inhibitors be used as the first line treatment?
So it's not fully immunotherapy question, but yes, yes, they could be used as a first-line treatment. You have to use it smartly. It means if you have uterine leiomyosarcoma, many of uterine leiomyosarcomas have estrogen receptor or progesterone receptor expression. They are different from the typical uterine cancer. What it means, that although they have expression, they don't, or breast cancer, they rarely depend on hormones for its growth. So yes, we had in typical uterine leiomyosarcoma responses to aromatase inhibitors are like in the range of 5% really. So there will be few that depend, but most of them lost this dependence, and chemotherapy is a better choice. But you can try and use it. Especially if you have a slow-growing tumor and say, okay, you know, it's growing so slowly. If you respond, and let's try it for 3 months, you didn't, then we'll switch you to chemotherapy. If you have rapidly enlarging tumor, probably this is not a good choice. PARP inhibitors will be the ones which could be used in the beginning if people have germline mutations or typical BRCA1, BRCA2 mutations, because these are the tumors that might be sensitive to PARP inhibitors, so there could be a choice. Yeah.
Thank you very much. Then we had another question, and you already highlighted some of the new immunotherapies that are available. Are there any others coming out that you haven't highlighted so far? And is there anything that you're particularly excited about that you think, oh, this is going to be an absolute game changer?
Yes, so I have to say right now we don't have any particular for leiomyosarcoma that is okay. Next year it's going to be approved, and this is what's going to change the landscape. We are excited about the new antibodies. I showed you one. We'll see what will be the follow-up. But what I have to say, I personally think that probably we already understood the magnitude of benefit of PD-1 blocking antibodies in leiomyosarcoma. It's going to be small. So we have to use different approaches. We are as I showed you the last slide, we are in the bottom group. We have to try to find the targets on the surface of sarcoma that differ from normal cells, and use CAR T cells, or the T cell receptors, which I showed in synovial sarcoma. These are the therapies. We are doing our own CAR T cells. Leiomyosarcoma patients can be also enrolled, although our target is rarely expressed in leiomyosarcoma. So we treated one sarcoma patient, but it was not leiomyosarcoma. But there is a lot of effort to try to differentiate what target can be on cancer cells and not on normal. And I think this will be the way for future for leiomyosarcoma, the cellular therapies with modification of the cells rather than another antibody. Hopefully I'm wrong.
Okay, and then there was another question about DNA sequencing and the importance of this, and how that helps with treatment.
So generally speaking, for immunotherapy, DNA sequencing is less important. I think the sequencing, or what we call next generation sequencing, would be important for different tumors, because it allows you to understand what mutations your tumor has. There is one thing which we get from the sequencing which can be helpful, is something what's called tumor mutational burden. So we see that some cancers can grow very fast, but they don't form mutations very often, and these ones respond less frequently. But if your cancer may not grow very fast or grows fast, but forms a lot of different mutations, so the mutational burden will be high. These are the ones that are higher chances to respond to immunotherapy. So this might be the benefit. But by itself, particular mutations which you got from DNA sequencing are not helpful with targeted therapy, maybe helpful with chemo, less helpful with immunotherapy.
Thank you. Are there any burning questions from the room? We've probably got time for about one or two. I just wonder. Okay, 1 second.
So there were a lot of trials that were, about immunotherapy and LMS. I just wanted to know if any of the inclusions for them, or if they were ever stratified for tumor markers or the tumor mutational burdens.
So the simple answer is no. It was not used as entry to this initial clinical trials. By the way, one comment about the clinical trials and continuation to what Dr. Chava says. People who have leiomyosarcoma, it's a rare disease. Clinical trial is always a good option for a patient with rare disease, because what we see, we have therapies, they are not great, so if the new therapies can be tried, this is always a good option. My assumption is, if you want to say, yes, I might consider clinical trial, try clinical trial as early as possible. So it means, sometimes it might be even the first line. It's not only inclusion-exclusion criteria, but if God forbid your cancer grows and you are in a worse shape, you will become, clinical trial will not be a solution. You want to be good, in a good shape with few symptoms, and then try clinical trial, because you can go to standard chemotherapy or whatever therapy always afterwards. So my assumption is just a message: if you have a chance for clinical trials, you have it available, try as early as possible, because clinical trials might be a better option than standard therapy.
Thank you. And I think there was one here. And that's it.
On the topic of adoptive cell transfer therapy that you mentioned earlier, right now there's CAR T cell, there's FAP-CAR, there's all the things that are along the lines of taking T cells out, harvesting T cells, educating them, and reintroducing them. But right now, from what I'm given to understand, there are a number of manufacturers, including like Numab and the like, that are coming out with different antigen therapies that are not available yet. I mean, they're just coming out now, phase 1, first in human trials. But what these do, as far as I'm given to understand, is that they will bind to specific proteins if they're being expressed by the cancer. And many sarcomas do express some of the ones that these are being offered through. And they enable your T cells then to recognize the existing T cells in your body, not engineered ones, not reintroduced ones. What's your opinion on T cell enabler therapies that are on the horizon?
Thank you, Darryl.
It is very exciting. It's because it's again in a different method, different way of thinking, and we know that there is interaction between the immune system and cancer. But still, whatever we have available right now, it's not sufficient. Definitely, I would say, to be mild. So, if you can enable your T cells, you have to bring them to proximity of the cancer, because if you enable them in proximity of your lung, that will cause inflammation of the lung. But yes, it's exciting.
Thank you very much. So this is a question that I will be asking all of our presenters today, and is the last question for you. If you had an infinite pot of money, what would you do with that money? And Dr. Singh, that will be coming to you later as well as a question.
Yeah, so I think, for immunotherapy, what it is, if we had an enormous amount of money, then probably the most important part is to invest in tumor testing in people on therapy. So no matter what therapy you have, especially if you are going on immunotherapy, if we could do biopsy before, and if the patient, so if you go on a clinical trial and there's an optional biopsy, unless you really say no, say yes. Because this will lead to the progress of further research. If we can see what happened to this tumor on the biopsy before and biopsy after, and see how the immune system interacted, why this tumor responded and the other didn't, it will lead to the progress. So we really need to invest this money, right? We did in the lab, we took it to the clinic. Now we have to take it back from the clinic, what we see, our successes and failures, and take it back to the lab so we can analyze to understand why some tumors respond, some don't.
So as a biopsy test, what would they be What would they be checking? So are we talking about a whole genome sequence?
Really for immunotherapy, we say we would look at mainly what immune cells infiltrated the tumor, which ones are excluded, what are the markers of the immune systems. Because I didn't go into details, not every cell in the immune system is equal. Some are exhausted, some are active, some are memory cells. How can you switch between this population? So it will be sequencing, but not necessarily the genome sequence. Will be more of gene expression profiles done, and also immunohistochemistry, so the markers on the surface and typing of the cells.
Okay, so is it worth the patients pushing for that in the very outset, even if their oncologist isn't willing to do that biopsy testing for them? Could they do it privately? Is that something that's an option?
So the simple answer is yes, you can do different biopsies and different testing privately. none of them are right now meaningful for selection of immunotherapy. So this is, I would say it's sequencing for your next generation, sequencing to try to understand what mutations your tumor have might be helpful to understand your tumor will help some percentage of people with selection more of a targeted therapy or chemotherapy. At this point, it's not so helpful with selecting immunotherapy. But I encourage people, if you're on a trial and you do and contribute, this will advance the research.
Trial.
Yeah.
Brilliant. Thank you very much. Can we all say thank you?